This is a yes.
So how many points we're losing if we just put the inch square? How many lose?
Half a point.
Okay.
No. The end of class today. Okay. So we're starting chapter 2. I'm not going to beat around the bush. This is not an exciting lesson. Everybody pay attention. Okay. We're getting ready for proofwriting in chapter 2. Okay. So in order to get ready for proofwriting, we have to learn about conditional and biconditional statements, which are sentences. So you may feel like you're in, I don't know, 5th grade English class or something.
Oh, not English. I hate English.
But nevertheless, you will see some mathematics involved, also identifying truth values of these statements. So the first vocabulary word is a conditional statement. A conditional statement is a statement that is in the form if something, then something. So if ... then ... And you'll fill in words or phrases between those dots. The notation is an arrow. P arrow Q stands for an if-then statement. P would be the hypothesis part we'll talk about in a second, and Q is the conclusion. So the example that's on our notes says, if you are not completely satisfied, then your money will be refunded. So this is a conditional statement. This part, when you see the variables, this would be like the P. This would be the Q. The arrow always goes where the then would be in the sentence if you were doing it symbolically. Okay. In the homework, you'll see something like this. So the hypothesis is the part that comes after the word if, and the conclusion will come after the word then. And that's what we have on our next slide. So the hypothesis is the part following if. The conclusion is the part following then. So you are not completely satisfied is the hypothesis. And your money will be refunded is the conclusion. Now, the mistake students make is they're like, hypothesis always is the first thing and conclusion is always the second. That's not necessarily always going to be true. Why? Conditional statements can be expressed in any of the following ways. So instead of just saying this is how you'll usually see it, if P then Q, you can also rearrange it to make it sound better. You can say if P, comma Q. So, for example, if you are not completely satisfied, comma, your money will be refunded. Same thing, right? You could also say Q if P. So, for example, your money will be refunded if you are not completely satisfied. So this is the one that you have to kind of pay attention to, because the conclusion actually comes first, and the hypothesis comes second. Now, if you use the definition of the hypothesis, it's whatever follows the word if. You should still get it right, but just pay attention. And then you also can get really fancy. P implies Q, or P only if Q. Okay. All right, so instead of having to write all these out, let's just circle. Let's do a little code so you don't have to write these. Okay, so the hypothesis, let's put a box around it. And then the conclusion, let's put a circle around it. And if you want, label them H and C, so you don't have to rewrite them out, okay? Just to save us a little time. So it says, if today is Thanksgiving Day, then today is Thursday. So what is the hypothesis? Yes. You don't want to include the if, actually. So it would just be that today is Thanksgiving Day is your hypothesis. And our conclusion then would be, Abby? Today is Thursday, so we'll circle that, and I'll put C. Okay, what we were going to write there is just write that out, but just to save us time. Now, the next two you'll notice are not in the standard form of if-then. Who thinks they could identify the hypothesis of this one? Peyton? Yes, here's the word if. Again, it will come after it. Now, if you were actually writing this out, you will see that I didn't use the word it, because you have to kind of say what it is. So I actually would say a number is an integer, but you are correct. This would be the hypothesis. The conclusion is a number is a rational number. Okay. And then the last one, similar. A number is divisible by 3 if it is divisible by 6. Abby?
It is divisible by 6.
Good. It is divisible by 6, or a number is divisible by 6 would be my hypothesis, because it comes after the word if. And a number is divisible, oh, I did that backwards. I said we were putting boxes around the hypothesis. And circling the
This
conclusion.
seems pretty easy so far.
Okay. Now below they're going to give you a statement, and they're going to ask you to write it as a conditional statement. So we need to write it in the form if then. Now if you want, you could also get fancy and put like Q if P, P implies Q, like you can write it however you want. But most of you will write if something, then something. So for example, it says, an obtuse triangle has exactly one obtuse angle. So to make this into a conditional, the easiest way to do it is to use your if then. So you're just going to say, if a triangle is obtuse, or if you have an obtuse triangle, then it has exactly one obtuse angle. So I had, if a triangle is obtuse, then it has exactly one obtuse angle. And again, sometimes you can get a little creative with how you say them. And then we will learn about biconditionals, where the order in which you write them doesn't matter. Now the next one is like a Venn diagram with a circle within a circle. So for this one, you will want to start on the inside circle and work your way out, because if something is a blue jay, it's also a bird, because it's in the bird circle as well. So I have, if something is a blue jay, then it is a bird. Or you could say, if an animal is a blue jay, then it is a bird. Again, riveting stuff today. But we are going to learn about the converse on the back, which we're going to use a lot of the converse in chapters 3 and 4 when we're writing our 2-column proofs. So it is important that we kind of get all this down now. All right, C, who could tell me what they would write as the conditional? Two angles that are complementary are acute. Who could write that as a conditional statement? Rachel?
If two angles are complementary, then they are acute.
Yep. If two angles are complementary, then they are acute. Because we know complementary means what? Rachel?
If I'm a right angle.
Yeah, they sum to be 90 degrees. So together they would add up to be a right angle, which is...
Please excuse the interruption. Tyler Weller, please report to the Welcome Center. Tyler Weller, please report to the Welcome Center. Thank you.
And then the next one can be a little weird because some people will be like, if a tiger is an animal, then it is an animal. Doesn't sound right. So I will say, if something is a tiger, then it is an animal, just so we don't reuse the word animal in the hypothesis and the conclusion. Again, some of these are just real weird. But you can't say animal in the conclusion and use that same word in the hypothesis. All right, now the back we're going to look at the converse. No, sorry, not first. We're going to look at the truth value first. So you will actually be identifying whether or not these conditional statements are true. Okay, so it has a truth value that is either true or false. Now it's only going to be false when the hypothesis stays true and the conclusion is false. So let me give you an example of that. If it is period 9-10, then I'm in English class. Okay? So you have to keep the you're in period 9-10 part to be true. We're not in English. Right? So then the whole conditional becomes false. To prove that it's false, you only need to find one counterexample. Okay? Counterexample would be that word in honors geometry. But sometimes there are lots of counterexamples. Sometimes there is going to be just one that you'll have to think about. So this is where we'll see a little bit more math.
Excuse the interruption.
Not the first
Brennan
one.
Wade, can you report to the guidance department at this time? Brennan Wade, to the guidance department at this time.
Show that the conditional statement is false by finding a counterexample. So they're telling you these are false. You don't have to think about them. They are false. If it is February, then there are 28 days in the month. So again, you have to keep this part the same. You're not allowed to change and say, oh, it's March. Like, February has to stay. What would my counterexample be? Lucy? Yeah, there can be 29 days in a month. Leap year. Okay, so up here is an old slide. It's the last leap year, but since then we've had 2016. So you really just need to put leap year. The leap year is going to get you 29 days in February, not 28. All right, now we'll get into more mathematical ones. If two angles are acute, then they are congruent. So again, keep the angles acute, but show me two angles that are acute but not congruent. Lots of answers here. Jade? 20 degrees and 30 degrees. I think I have 25 and 35. As long as they're both less than 90 and not the same number, they're a counterexample.
Wait, we don't have to write all that? Like we stated?
No. This is just to find the counterexample. All right, and C. If x squared is greater than or equal to 0, then x must be greater than or equal to 0. Colby? Any negative number. I chose -2. Okay. Because it would keep this part true. 4 is greater than or equal to 0, but -2 is not greater than or equal to 0. So again, you always want to leave the hypothesis alone. You're just trying to prove the conclusion false with a counterexample. Excellent. All right, now here we are with the converse. So what the converse does is it takes the hypothesis and the conclusion, flips them. Okay? So once we flip them around, the if stays where it was, the then stays where it was. You just move the actual statements. When we do that, the truth value may change. Okay? And the converse is something we're going to see a lot in chapters 2, 3, 4 when we're writing our proofs. Okay, we'll have like, if two lines are parallel, then corresponding angles are congruent. Then we'll also be able to use the converse, which will say, if corresponding angles are congruent, then the lines are parallel. So we'll be able to prove it both ways. The notation, the original statement you remember was P arrow Q. So the converse is going to switch those to be Q arrow P. Again, P would just stand for like a part of a statement. So, example 4 says to write the converse of the following conditional statement. So a lot of students like to identify the hypothesis and the conclusion. If two lines intersect to form right angles, then they are perpendicular. So all we're going to do to write the converse is we're going to flip those. Now, the only thing you have to be careful of is you don't want to take the word they and put it in the beginning of the sentence when we have no idea what they is talking about. So you would want to actually keep the two lines part where it is. So you would say if two lines are perpendicular, then they intersect to form right angles. If two lines are perpendicular, then they intersect to form right angles. And who thinks they could tell me the converse for B? If two lines are not parallel and do not intersect, then they are skew. Rachel?
If two lines are skewed, then they are not parallel and do not intersect.
Perfect. If two lines are skew, then they are not parallel and do not intersect. And the last one at least has less writing. Who could tell me the converse of our last one? Ashley?
If X is greater than 12, then S is not.
Perfect. Around. below is we're going to also identify truth values with each of these. So the big thing to remember is that just because the original statement is true, the converse is not necessarily true, and vice versa. If the conditional statement was false, when we flip it around, it might become true. So that's what our next little part says. If a conditional statement is true, its converse could be true or false. You have to test it and think through your counterexamples. Now this next part I'm going to skip over because I think it's just going to confuse you more and you don't need to know it except when we're doing our truth tables, which you would get to in advanced algebra senior year, but we'll skip over it. So the example 5 below asks us to write the converse and determine the truth value of both of them. So I'm actually going to switch the order in which we do this. Let's read it first and identify if this is true or false. If two lines do not intersect, then they are parallel. Okay? Now before you reach out and tell me true, I want you to think, is there any type of line that does not intersect that is not parallel? So you're trying to think of a counterexample. Oh, look at all these hands. Come on. Skew lines. Okay? So this is going to be a false statement. And again, the reason is that it is false is that they don't have to be parallel, they could be skew. Okay, so you always want to try, you have to leave the hypothesis alone, you can't change it. But the conclusion you're thinking, could it not be parallel? Alright, now let's write the converse, Who could tell me what the converse of this statement would be? Converse. Noah?
If two lines are parallel, then they do not intersect.
Good. If two lines are parallel, then they do not intersect. If two lines are parallel, you could use the symbol too instead of the word. You want to use your parallel symbol. Perpendicular, you can also do that. And then you not intersect. Is the converse true? Yes, it is. The definition of parallel lines are two coplanar lines, technically, that do not intersect. So if two lines are parallel, then they do not intersect. That is true. So sometimes you could have both of them being true. Sometimes they'll have alternating truth values. Okay? So you just have to check. All right. Let's test this one first. If x equals 2, then the absolute value of x equals 2. Is the original statement true or false? Be careful. Be careful. Be careful. Be careful. It is true. Now some of you that are saying false are thinking -2. That is going to be the converse. That'll be your counterexample for the converse. The way it's written right now says if x equals 2. So again, you have to leave x equals 2 as is. You can't change the hypothesis. So if you take the 2 and you plug it in, the absolute value of 2 is 2. So this is true. Now when we flip it around and we write the converse, which will be if the absolute value of x equals 2, then x must equal 2, this will be false because of the -2. So just be careful because the order matters. You're not allowed to change the hypothesis, the first part. You can't change this to be a -2. It has to stay. The only thing you can modify it or see if it changes is the conclusion. And again, that's because if I were to plug in -2 here, I would still get 2. This would stay the same. And then how about C, the original one? If x squared equals 25, then x equals 5. Is the original conditional true or false? Colby? False. Okay, if I were to solve, it starts out with this part. We have to leave this alone. If I want to solve for x, I would square root both sides. The square root of 25 is actually positive and -5. So it doesn't have to be 5. It could also be -5, so it's false. Then we write our converse, switch it around. If x equals 5, then x squared equals, this should say 25. Is the converse true? If x equals 5, leave this alone. If I plug 5 in, 5 squared, does that equal 25? Yes, that is true. Okay, try the closure, which asks you to write a conditional write a converse, and identify truth values. While you're doing that, I'm going to pass out your homework.